RF systems rely on a tightly connected set of mathematical tools that describe signals, systems, and uncertainty in a unified framework. Without these concepts, modern communication technologies like wireless networks, radar, and satellite links cannot be properly designed or analyzed. This final lesson summarizes the complete mathematical foundation behind RF engineering. Signal representation in RF engineering begins in the time domain, where signals are expressed as functions of time showing how voltage or current changes continuously. This representation is physically intuitive because it directly corresponds to measurable quantities in real circuits and antennas. However, it often hides the internal structure of signals when multiple frequency components overlap. To reveal this hidden structure, signals are transformed into the frequency domain using Fourier series or Fourier transform. This transformation decomposes complex waveforms into sinusoidal components, each representing a specific frequency contribution. The frequency domain provides a clearer view of bandwidth, spectral content, and interference behavior. Together, time and frequency representations form a dual perspective system. Engineers switch between them depending on the task, using time domain for waveform behavior and frequency domain for system design and spectral analysis in RF applications. RF systems are not passive. They actively modify signals through filtering, amplification, attenuation, and distortion. To mathematically describe this behavior, convolution is used as the fundamental operation that links input signals with system response. This makes it possible to predict output signals based solely on system characteristics. The key concept behind convolution is the impulse response, which fully describes how a system reacts to a very short input excitation. Any real input signal can be decomposed into many small impulses, and the system's response to each impulse is accumulated over time to form the final output. In the frequency domain, this complex time-domain interaction simplifies significantly. Convolution becomes multiplication, allowing engineers to analyze system behavior more efficiently. This duality is essential in RF filter design and communication system modeling. RF signals are inherently oscillatory, which makes complex numbers a natural mathematical tool for analysis. Instead of treating sinusoidal signals as separate sine and cosine functions, they can be represented as rotating vectors in the complex plane. This simplifies both visualization and mathematical manipulation. Euler's formula connects exponential functions with sinusoidal oscillations, allowing signals to be expressed in compact exponential form. This representation captures both amplitude and phase information simultaneously, which is critical in RF circuit and wave analysis. Phasors extend this idea to steady-state sinusoidal signals, converting differential equations into simple algebraic relationships. This greatly simplifies the analysis of AC circuits, modulation systems, and RF signal behavior in frequency-dependent environments. Real RF systems always operate in environments affected by uncertainty, noise, and interference. Because of this, deterministic models are insufficient, and probabilistic methods are required to describe signal behavior under real conditions. Random variables are used to model unpredictable quantities such as noise amplitude, phase variations, and channel fading. These variables are characterized using probability distributions, which describe how likely different outcomes are within a system. Gaussian noise is the most important model in RF engineering because it naturally arises from thermal motion and electronic fluctuations. Expectation and variance provide statistical summaries that allow engineers to evaluate system performance under uncertainty. All these mathematical tools combine into a unified framework that defines modern RF engineering. Signal processing relies on Fourier analysis. System behavior is modeled using convolution, oscillations are simplified using complex numbers, and uncertainty is handled through probability theory. This integrated structure allows engineers to design, analyze, and optimize communication systems that operate reliably in complex and noisy environments. Each mathematical tool addresses a different aspect of RF behavior, but together they form a complete analytical system. Without this framework, technologies such as Wi-Fi, LTE, radar, and satellite communication would not be possible, as they depend on precise control of signals, systems, and noise behavior. In this lesson, we summarized the core mathematical foundations of RF engineering, including signal representation, system modeling, complex numbers, and probability. We also connected how Fourier analysis, convolution, and statistical methods work together to describe real-world communication systems. This completes the mathematics foundation for RF, forming the base for understanding all advanced signal processing and wireless communication topics. If you found this useful, like the video, subscribe, and follow for the next lesson.